series. This afternoon, we have the pleasure of hearing from physics professor, Dr. Marco Cavaglia. Dr. Cavaglia will speak to us on an interesting topic. His presentation, Missouri's Window into the Sky. This is research into what is called the dark side of the universe. Again, there'll be a few minutes at the end for Q&A, so please post your questions in the chat and we'll try to answer as many as possible in our allotted time. Dr. Cavaglia, the platform is yours.
Thank you very much. Let me share my screen and start the slideshow. Thank you very much for attending my talk today, for taking time in the middle of the day to listen to what we are doing here at Missouri S&T regarding astrophysics. So I have 20 minutes to explain to you Einstein's theory of general relativity, what are black holes, the work of 6 recent Nobel Prize winners in physics, and what we are doing in astrophysics here at S&T. So bear with me. I'll try to walk you through all of this. But let's start with the night sky. So if you go to a dark place, if you've ever been to a dark place, you can travel a few miles out of Rolla if you are in Missouri, and go to a dark place and look at the sky. What do you see when you look up? It's a great spectacle. You see all these stars, you see the Milky Way, and you may wonder what is up in the sky. What are these stars, and even what is our place in the universe? And if you have ever asked yourself this question, you are certainly not the first one, and you're certainly not alone. This is a story that started many years ago. This is a painting that dates back to the Paleolithic age. It's a painting that was discovered in France in a cave called the Grotte de Lascaux. And these were drawings made during the Paleolithic age, right? These are probably one of the first paintings that humankind has ever done. And when people, scientists looked at these paintings in detail, they found something amazing. You see in this drawing of a wild bull, you see these dots, and you can really relate these dots to stars in the sky. These 3 dots circled in blue can be matched with the Orion's belt, a very famous constellation that you can see right now in the evening sky. And these other dots, you can relate them to clusters of stars that you also see in the sky, like the Hyades and the Pleiades. So about 17,000 years ago, people were already looking at the sky and wonder what's up there. And the story continued through the ages. This is a star map that dates back from 700 AD in China. It's called the Danhuang star map. And we can already recognize all the constellations that we are familiar in the sky, like the Big Dipper here, Cassiopeia, the Dragon, and so on. And people have been looking at the sky and wondering what's happened, what's up there, what are these objects? And I originally am from Italy, so I had to put something from my country. And this is a fresco by Giotto that you can find in Italy. And you see what's here on top. This is a comet, right? This is the comet that is associated to the visitation of the three kings after Jesus' birth. And what you can see here in the 1300, Giotto paints this comet really as he saw it in the sky. He actually happened to see Halley comets a few years before he made this fresco. So he depicted this comet in a very realistic way. It's the first time that in history in paintings you find an astrophysical object that it's really depicted as you see it in reality and not in an abstract sense. And things started really to change in the 1600, thanks to Galileo Galilei. He was the first person who used a telescope to look at the star and doing science, doing what is we now call modern astronomy or modern astrophysics. And in about a couple of months in 1610, he looked at all the objects that he could see in the sky and took notes and made the first really astrophysics papers, modern astrophysics papers as we now understand. And he discovered amazing things. He discovered that the moon has mountains and craters. He discovered that there are many more stars than what we see with naked eye. And what we see as a fuzzy stripe in the sky, the Milky Way, is actually a lot of stars together, right? That the naked eye cannot discern, but you can resolve with even a small telescope. He found out that the planet Venus shows phases like the moon, so it means that it's orbiting around the sun. He found that Saturn had a strange shape, so he thought Saturn was a planet with 2 years. And this is what now we know they are rings. He found out that the sun is not that perfect Aristotelian object, but is actually has spots. There are dark spots, and that the sun rotates. And finally, he discovered that Jupiter had 4 moons orbiting around it. So this really gave him the proof that the Copernicus way of describing the solar system with the sun at the center of the solar system and the Earth rotating, orbiting around with all other planets was the correct one. And this is an ancient old Italian, right? I can still make up a few of these words and so on. And it's amazing to see the excitement of Galileo in doing these discoveries. Now, this was 300 years ago. So we have gone a long way since then. And we know much more about astronomy and astrophysics. We have landed on Mars many times. We have orbited around, machines have orbited around Saturn and all the planets of the solar system. Now we know what is the dynamics, what's the physics of these planets. We observe the sun in different wavelengths. We understand what's happening in the sun, how the sun produces its energy, and how it evolves with time. And we even peek further in the universe, billions of light years away from Earth. We see colliding galaxies. We see star formation. These are called the pillars of creation. This is a region in our galaxy where new stars are being born right now, right? So in a few million years, this region will appear as a star cluster of very young and bright stars. And these galaxies that we observe, and we observe millions of galaxies in the universe, each of them contains billions and billions of stars. Just our Milky Way, the galaxy we live in, it has an estimated 500 or 600 billions of stars just in our galaxy. And we observe millions and millions of galaxies across the vastness of the universe. Now, what is our role here at S&T in all this evolving story? So since last year, we have a new institute here on campus. It's called the Institute for Multi-Messenger Astrophysics and Cosmology. And I would like to spend a few words about what we do here. Until 2018, there was no astronomy or astrophysics here on campus. Now we have a dynamic group of people who do astrophysics and study these wonders of the universe. We have postdocs. Some of them work here on campus. Some of them work off campus at astronomy facilities and detectors. We have a group of young and excited graduate students working on different aspects of astrophysics, from exploding stars, supernovae, to gamma ray burst explosions in the universe, to detectors and black holes. And then our institute hosts undergraduates, affiliate members, high school students, and we collaborate with thousands of people, of scientists worldwide. So what do we do here? We do some cosmology, and we also do some multi-messenger astrophysics. So what is multi-messenger astrophysics? Well, I told you a few minutes ago that modern astronomy started with Galileo using a telescope, a new instrument to look at the sky. And since 2015, we have we as humankind, have built a new kind of telescope that is called LIGO. LIGO is short for Laser Interferometer Gravitational Wave Observatory. And we have actually several of them around the world. My group collaborates with two of them here in the United States. They are twin detectors. One is in Washington State and one is in Louisiana. They are identical, they are twin detectors. Here in the picture, you see one of them, the one in, well, you can guess, the desert of Washington State, of Eastern Washington State. What are these instruments? So I told you these are a new kind of telescope. These are instruments, detectors, that measure, observe gravitational waves. So gravitational waves are ripples in space-time that were predicted by Einstein over 100 years ago. And it took a while to detect them because they are very tiny and their effect is very small. What are these gravitational waves? Well, you have to imagine that when there are objects in the sky like black holes or stars, and they are orbiting one around the other, by doing so, they curve the space-time and they really stretch and compress the space that is around us. So when I say stretch and compress, you have to imagine the space-time, as really a fabric, as a rubber sheet, right? Something that you can deform and warp. And what is doing that is the energy that it's containing. So when in the sky we have objects like black holes that merge together, they collide, or exploding stars, or other really cataclysmic phenomena, what happens is that they generate these waves that propagate in space. And this is a new instrument that allows now to see them and measure them and understand their physics. So let me just show you briefly, just to give you an idea how these instruments are. First of all, they are huge telescopes, right? So they are over almost 3 miles in length, perpendicularly in two directions, so about 4 kilometers. And they use a laser, a very powerful laser, to measure the deformation of the space-time that is generated by these colliding black holes. In practice, what they are is they are gigantic rulers, right, made with laser light and mirrors to measure how the space-time warps when a wave passes by. Now I'm going, these are some pictures of the instrument. So everything is in a almost perfect vacuum. These mirrors required a feat of engineering and years and years of study to make them, including patents for coating and new techniques that needed to be developed to build this instrument. This is really the state of the art that we can do now as a measurement devices. So let me tell you a little bit what we do with this and what we measure. And after Galileo, I would say the next big step in the history of astrophysics physics happened 5 years ago, 5 years and a month ago, in the early morning, US time or our time, when for the first time our twin detectors recorded the whisper of a colliding black hole that two colliding black holes that happened over 1 billion light years away from us. So that event happened 1 billion years ago. And this whisper, this deformation of space-time traveled across the universe, across galaxies, across the vastness of space to reach us and give us a signal and telling us what happened. And I'm going to play a clip of what the instrument recorded. And this whisper, this gravitational wave, is played 4 times, twice like the original sound and twice as an enhanced version, so you can hear it better. So if you have good speakers and good hearing, towards the end of this clip, you hear like a whisper, like a whoop. This is the sound translation of a wave of space-time created by 2 colliding black holes. And as I said, this was predicted by Einstein in 1916. And the theory of general relativity, in a few words, what it tells us is that you can bend the space, you can bend the space-time, you can curve it. And what's the origin of the curvature of space is the energy and the mass. So for example, the sun curves the space around it. And the Earth and the Moon and all other planets orbit around the sun because they follow the curvature of the space, just like these objects are depicted on a grid, right, that can be stretched and compressed and curved. So the old idea of Newton's gravity, of this mysterious force that we don't know why exists, is simply reconciled with the geometry of the universe. So again, the space is really an entity. It's not something we can touch with our hands, but it's something physical that you can deform, you can bend, you can play as if you have enough energy. And so what LIGO measured was this bending, this wave of space that traveled, as I said, across the universe. And this is a simulation of the event of 5 years ago, as we observed. These are two black holes, so two regions of space that are so dense that not even light can come out of it. So these are really trapped regions of space. Space is so curved, so bent, that it curves into itself and nothing can come out of it. And these two black holes happen to be in a pair, and by rotating and losing energy, orbiting one around the other, and getting closer and closer, eventually merge to create a single black hole, a single very dense object. This is the moment where this happens, where these two event horizons uh, merge together. And in doing so, they curve the space-time. What you see here at the bottom is the curvature of space-time, emitting these waves that propagate across the universe. And when these waves propagate across the universe, they can reach us, they can reach Earth, and deform Earth, deform the space where Earth is. This, of course, is vastly exaggerated, but this is what happened on 2015, right? So this wave of space, this signal that was never observed before, finally reached Earth and was measured by our two instruments. This is the actual signal that we measure in the instruments. And this is a picture of us announcing it to the world on 2016 in DC. And the whole world, right, went abuzz with the news that we proved Einstein right. And 1 year later, my three friends and collaborators that first started this project, Ray Wise, Barry Barish, and Kip Thorne, they were awarded the Nobel Prize in Physics for this discovery. And I'm pleased to say that Ray Wise will give a Zoom talk at for us at Missouri S&T on November 5th. We'll advertise it. He was kind enough to come and give a Zoom talk for us. So please, everybody of course will be invited. This is another simulation of what we discovered. Before 5 years ago, we didn't even know that for certainty that black holes existed, right? And that they could orbit one around the other, and then they could merge to form a larger black hole. If we could have been there nearby these two black holes, this is what we would have seen. These two objects, completely dark because they don't emit light, orbiting one around the other, closer and closer, at the speed of light, right? Almost at the speed of light by the time they merge. And they warp the space around them. So even if you have stars in the background, you will see them bending and flying around, following the curvature of the space-time. Now, we know a lot about black holes. There is a lot that we don't know, but we know now that the black holes do exist. They come in any size, right? The one that we discovered that we measured, the first one that we measured in 2015, had only a diameter of about 370 kilometers, right? This is about 200 miles. So it would well fit in Missouri, right? Much smaller than the Earth. We know that there are black holes that have a mass of billions of solar masses. So their weight is billions of times the mass of the sun. We even discovered, right, gigantic black holes that have a huge mass. And we know more or less how they form. They form in star explosions. We observe these star explosions. We even know that we have one gigantic black hole at the center of our galaxy, at the center of the Milky Way. And this discovery was recognized with this year's Nobel Prize in Physics to Reinhard Genzel, Andrea Ghez, for the discovery that there is a black hole at the center of our galaxy. So I'm going to play this briefly. Again, I'm running out of time. What you see here, this is a track of all the stars that are at the center of the Milky Way. And you see that they are orbiting around something that is obviously there, but you cannot see. And this is a black hole that has a mass, an estimated mass of 4 or 5 billion solar masses. So there is this behemoth there at the center, dark, that from time to time absorbs some stars and some objects, emits flashes of high energetic radiation, and all these stars eventually they will fall into this black hole. So back briefly before I conclude about the research we do here, we work on these topics. We use machine learning and new techniques to analyze the data of the LIGO detectors. We publish papers about cosmology and trying to understand what is the physics of these black holes. We work to make these detectors better and better. And make them more sensitive so we can understand more about these objects that are in the sky. At the same time, we like to do outreach and get involved with education. So now is a bad time with COVID, but we like to give talks in school, go and talk to people, explain what we are doing, do demonstrations to make this obscure branch of physics more understandable to everybody. We really enjoy this. This is one of my graduate students last year at the Science Fest Engineering Expo in St. Louis at the St. Louis Science Center, explaining the curvature of space-time to a budding scientist. Okay, so just to wrap it up, this is a quote that I found a few days ago on BBC News on an article about the Nobel Prize in Physics for the discovery of the black holes at the center of our galaxy that I mentioned. And I found it very illuminating. So 100 years ago, we didn't even have the theory of space-time. And then over the decades, people worked out the mathematics of black holes, the mathematics of general relativity, and told us what to look for in the sky. And finally, we were able to measure, to observe these black holes, to detect gravitational waves, and we start mapping how many of these objects there are in the sky and so on. This is just the last chapter in that story that started in the Paleolithic age, in the cave of the Lascaux. So science continues, astrophysics continues. I'm pretty sure that if I have to give this talk next week, there will be something new, something more that we know about black holes and about astrophysics. And thank you very much for listening.
Thank you, Dr. Cavaglia. We've got a few moments. If anybody would like to ask any questions, we'll hang on for just a couple more minutes. I know we try to keep this to half an hour, but that was a great presentation, and I really enjoyed seeing some of that. A lot of comments in there that people are saying it was awesome. Thank you very much. Excellent. Very interesting. So we'll hang on till for a couple more minutes and see if anybody's got any questions. Dr. Cavaglia, did you see the one that popped up?
Yes, I can see. So I think the first one is what could happen after black hole absorb too much energy? So black holes can grow. They can absorb mass and energy. We actually observe in the sky events where stars can be eaten by black holes. So part of the matter of these stars, for example, is converted into energy, is converted into gravitational waves that are pure energy. Some goes inside the black hole, and we don't actually know what is inside the black hole. We have some mathematical theory, but we actually do not know. Some other matter can escape and becomes very, very hot, becomes very, emits a lot of radiation, and we can see these flashes in the sky, like, for example, this one is at the center of our galaxy. So we are still learning about what happened, both from the mathematical point of view and from the observation point of view. Since the blip of the gravitational wave was so small, how do we know it wasn't caused by something else? Excellent question. So it was very small because these two black holes collided on the other side of the universe. So by the time that energy comes here, has been traveling all across the universe, so it's very tiny. So we know that it is from astrophysics because we have two detectors. So we work in stereo, right? So they detected the same thing at the same time. So it could not be anything that was terrestrial in origin. And also they saw exactly the same thing. And by looking at these signals and matching them with the theory, we can tell almost exactly where this event happened and how it happened. But one thing that I didn't mention is that these things are really tiny, right? So they deform space here on Earth just by 1/10,000 the size of an elementary particle of a proton, right? So it's the equivalent of changing the distance between the sun and the Earth, which is 100 million miles, by the width of one atom. That's the precision that we need to achieve to measure this. I see comment. Yes, it's in LIGO. The LIGO detector in Hanford is in the nuclear reservation in Hanford, Washington, right close to Richland. So this is the picture there. It's a wonderful place to visit. Let's see. I see Kelly. I'm a high school teacher in Lee Summit. I teach astronomy, and I was wondering if you would be interested in speaking with my class at some point in time. By all means, yes. I enjoy doing that. I'll be happy to do that. And if you want somebody who is younger than me for your students, my graduate students can do it with me, or can do it by any means. You can contact me through email if you go to
Dr. Cavaglia, I'll put you guys in contact. I have
okay,
when Kelly registered, I have that, and so I will do a email and we'll get it taken care of.
Perfect.
We'll get you two in contact.
And I have Kelly's email, so we are good. Okay, Mars is in opposition, so look up. Yes, if you look south, early evening, you can see a very bright red star. It's Mars. It won't be as close until I think 2035, so don't miss the opportunity. Robert, yes, perfect. Sounds good, Robert.
Again, thank you, Dr. Cavaglia. We really appreciate you taking the time out to join us today, as well as our audience. We know your schedules are packed, but we appreciate you taking a lunch break or just a break and joining us. So thank you.
Thank you very much.
Great. Have a great day, everyone. Please join us next month for the next speaker series event. Take care.